Okay, so we'll get started. This is the last class, and then next week you're going to have exam. So let's get, as I said, how many of you have seen Piazza and know what the agenda for today is going to be? Okay, so as I said, I'm going to basically do like a lecture on transformers and attention because a lot of people wanted to know about it. So that's like the main middle of the class. And then there's a little administrative stuff, and there's also sort of a full goodbye in the end. That should be hopefully very, very short. So the administrative stuff, the homework 5 is due on 11:30, and the solutions would be posted pretty soon after that. I think there's only a couple of people who wanted like taking an extension or something. So basically they will be posted by the weekend. There's going to be a reflections notebook assignment that I will tell you, but basically that involves concatenating all the course reflections at the top and then all the other classes in the alphabetical order. And then we'll probably ask you to write a table of contents of which particular classes you actually have the notes for. We do have a way of figuring out, but I think it'll be easier to do it that way. I'll let you know exactly what you need to do and where you need to drop them by today or tomorrow. I'll send them out. It's just basically mindless work of just taking your own posted comments on the reflection notes. Okay, but that gives me an idea, when I'm trying to make sense of what your grade should be, etc., when everything else is more or less similar, etc. For example, I would look at what people have done in terms of what have they done in terms of the course. The final exam itself is exactly next week, right? So 12:05, but remember it is 2:30, not 3 o'clock. And it's a 1 hour 15 minute, actual long exam, 1 hour 50, instead of 1 hour 15. So, and then they'll have basically 2 parts. One would be sort of problems of the kind that you looked at in the first midterm. That would only be from the stuff that happened after the midterm. So after reinforcement learning, and the second part would be like across the semester. It'll be a true and false questions, a bunch of true and false questions, but with negative marking. Okay, so if you're not sure and you just randomly toss a coin, you take a penalty. Okay, and so actually, I think in fact, if you write justifications and we have to read the justifications, that becomes very hard. And so we're just going to do it that way. Yes.
Is it in this room?
You sit in this room. Exactly. It's in class right here. Okay. That and the true false part will be drawn from the entire semester. If there's any changes to this, I will let you know. Follow the Piazza. And then finally, the Fulton course evaluations are still going on. As I said, those are completely different from the course reflections that you have already put by yesterday night. We'll talk a little about those later on. But the Fulton course evaluations is your way of telling anonymously, how the course was and what you enjoyed, what you didn't, etc. It's not about so it's basically that's your way of giving the feedback. And as I said, I will share it with you when they send it to me at the end of probably close to beginning of January. So about 43%, I think, of you apparently have completed as of today. They don't show us what you wrote, but they tell us what percentage of people have completed. 50 people, 50 people, as of 11 a.m., 50 people have actually taken time to complete the thing. So that works out to 43%. So hopefully the rest of you will find time. But remember that will close Thursday midnight. Okay, so that's about that. Any other questions on the administrative stuff? Yes.
What's the difference between you get a point right if you get the true and false question right versus negative marking?
So negative marking is when you are wrong, you don't just get 0, you get negative marks.
Okay. So it would be
that's what is negative marking. So for every question I'll give you the exact information on the thing, but so for every question that you get it right, you get full point. And when you get it wrong, you essentially lose a -1/3 or something. I'll tell you. Okay, that's just basically basically to stop people from guessing. But, I should mention, even though last time around when I mentioned this, people yelled at me in the Rate My Professors, but that there are psychological studies saying that men guess whatever the heck, and women tend to be much more careful. And so, so don't stop yourself. If you're close to the correct guess, you should take the chance, because it's actually, there is no such thing as metaphysical certainty. Okay. It's only don't toss a coin. If you think it's like 60%, you think it's true, then you should do it rather than just worry so much. Negative marks would not drown out the positive marks. So, but that's the thing. But on the other hand, it's very well known that this is another of these utility issues. $1 in penalty and $1 in reward are not the same for many, many people. You understand what I'm saying? So, in fact, I know that my wife considers $1 in penalty to be essentially minus infinity. It's like, in the sense, it's a society telling her that she didn't do the right thing. I just say, $1 penalty, some $1. I made $1 here, I lost $1 here. That's not the way many people think. Actually, they think that penalties are much more steeper. Remember, dollar is being converted into utility that you are your reward. And the negative side, it might be much steeper for some people. And so this is, again, things that are connected to the course anyway. But, I just want to bring that up, that try not to just stop yourself from answering just because you're not 100% sure. Okay. But this is to stop people from just tossing the coin. Yes?
Is it equivalent to plus one next one? If you get it right, it's plus one. You get it wrong.
No, obviously not. Have you guys never did negative work? I mean, I think the whole GRE, AGRE, etc. have that stuff. Yeah, GRE no longer does. Yeah, I think, yeah. But I will tell you the actual thing. It'll be like a third of the point you lose for all the negative points. Yeah. Otherwise, what's the point? It's not nice. Yeah.
JE advanced.
Yeah. Okay. JE advanced apparently has it. Okay. Okay. Q star Anon. How many people have been following the latest and greatest craziness of it's like one of these things where AI has become randomly standing outside of OpenAI headquarters and seeing if they are throwing out stuff or if they're muttering something and say, oh my God, that must mean that the AGI is coming. Anyway, so it turns out that nobody really knows what's talking, for those of you who have heard about these conspiracy theories, essentially there's this idea that maybe OpenAI came up with a slightly better idea for something, and then that might actually unleash AGI and will kill you all. So if it happens before the final, it'll be great for all of us because we don't have to take the exam and grade the exam, but I doubt it. But if you're interested, basically, it's, I kind of wrote stuff on the LinkedIn as well, and, on Twitter, if you want, you can follow that. But from the perspective of this course, it's really a brute force way to compute H star or Q star for all possible states and goal combinations upfront, and then use that. Remember, many a time I asked you guys, why don't you compute H star and then use it in A star? And you all laughed at me saying that would be solving the problem, much harder problem than the problem I'm trying to solve. You understand what I'm saying? However, if I give you a particular problem domain, and I'll say tons and tons of questions on this will be coming by random people, rather than solve it every time when people are, and then of course, once the people ask a question, they want the answer like right away. It may be worth your, and plus you have Satya Nadella's Largesse, and so you have, also GPUs, etc. So it might be worth your time to go ahead and compute the H star. Okay, or compute essentially the optimal behaviors from every state given any goal, and then use that to fine tune the LLM. Okay, that's basically what I write there if you follow that. And they use the word Q, but Q, A, everything is connected. You know that A star is essentially MDP for deterministic. And one of the things that you will notice, it's like hilarious. All these young folks who have completely ignored intro to AI that you're taking right now, relearning all this stuff. What is this stuff? So Devil looks like Q and A. And in fact, somebody even asked, so if it is A star, would it be even worse? like, alphabetically the highest, devil or something. But anyway, it's fun. So you, in some sense, you are now going to be part of this inside jokes because the world at large is essentially interested in trying to guess what's going on in AI, and more than most random people. Okay. Anyway, so that's basically about the QAnon thing. I mean, it's again, this is all mostly a conspiracy theory right now. Nobody really knows whether anything was done. But, if they could have done it, it's worth understanding that ultimately it's like having like a gold test outside. And with respect to the gold test, you are essentially trying to compute or verify it. You're trying to compute all possible behavior traces from any state to any goal combination. And then use all of this and then retrain, basically fine-tune the LLM. That's one possible way. We have no idea what they have done, but it's fun seeing this. Actually, I was getting like this guy from Wired calling me yesterday, trying to ask me, so exactly what do I think of this Q star? And so I might actually show up in one of the articles today. Okay. So that, by the way, is the, so you guys did the reflections, course reflections, and one of the things, the last question, I will talk about the rest later, but the last question was essentially, tell us what else do you wish has been done in the class, right? And different people have said different things. And first of all, I want you to know that if you should ask yourself the following question: How many of you think, look back at what you wrote in your course reflections and ask yourself, would I have written these before taking this course? And did I think that I already knew AI before taking this course? And it would be very interesting because many of you probably have changed the questions you're likely to wanted to know because you've taken the course. And that's essentially the, kind of an advantage of, you can have a more interesting, I wish we did this sort of a thing, as again as tell me more layers or neural networks. But, one of the things that many people brought up, several people brought up, although there's a diversity of topics that people wished were covered, as if there hasn't been, enough things done here, is, of course, we are talking about LLMs, and LLMs are run by transformer network. Transformers have this attention thing, and, what the heck is attention? Why is it the only thing that you need? I know that attention is all I need from you guys, but I don't know what you need attention for, really. So I'm going to talk to you about that. Okay, why the heck is it doing this? Let's go back and then go. Yeah. Okay, so it's still working, right? Yeah. So the way I will do it, first of all, it's a, normally you should do it in multiple classes. So I'm going to do it in like about an hour. Actually, I don't even have an hour really. So about 45 minutes. By 4 o'clock, I need to shift gears. So basically, I want to get you an idea of what is involved in transformer networks and self-attention, so that when you actually get into the nitty-gritty of all the details, you will at least have this connection that you have made to other things that have been discussed in class. Okay, the simplest way to think about it is think of, you did CNNs, right? You did ConvNets. You kind of think you understand that. The question is, if you wanted to do something like ConvNets to image, language, instead of the images to the language, how would it go about? How would you go about it? Of course, there is a dumb idea, which is take a picture of the text, right? And in fact, not surprisingly, many of you probably heard about DALL-E has hard time. DALL-E 2 used to have very hard time writing English in the images that it is synthesizing, because it doesn't quite realize that, English is not just drawing. In the language is not just drawing. It's a different symbolic, thing that we actually learn to communicate in, right? So let's compare them and say that in language, instead of pixels, we have words. Okay. And in general, actually, even though I would say language, because that's a lot more interesting, essentially, we are talking about spatial data, which is images, and sequence data, which are sequences of word, or sequences of Python code, or pretty much anything that gets sequenced, honestly. And it turns out that most of the intuitions behind transformers came from sequence of language sequence data, but they've been used for anything which is a sequence. They use it for music, for example, which is in terms of notes. It's like a sequence of notes, for example. Right? and all sorts of other things. So you realize that we have words instead of 2D organization of pixels, and instead of the 2D organization of pixels, you have 1D organization of words, just a long sequence of words. I mean, we kind of do some funny formatting, but really language is just a long sequence of words. And you know, if you consider punctuation also part of the words, then it's just a long sequence of words. Okay. The fact that words are discrete seems to be like a big difference upfront, because images have intensities that are real numbers. Essentially, images sort of seen as a big matrix of real numbers. The real numbers being the image intensities. And you can also do it in RGB intensities, but you know, you can just do it in intensity for gray color pictures. So for instead of pixel intensity, you have words. Words are discrete, right? By the way, how many of you have seen Arrival, the movie? Yeah. So first of all, you're smart, okay? And in general, just seeing that movie makes you smart. But the rest of you should watch it. It's a lot of interesting connections between what language and the structure of language, etc. It's obviously Ted Chiang is like an amazing science fiction writer. He's basically based on a single short story of him by him. And in some sense, there is this whole thing in linguistics and in a language that does language affect your thought? The way you think about, is it going to change because of the language you speak? Right? I speak in 3 languages, so I think in 3 different ways. Most of you also speak in maybe 1 language, and so you should barely think in that language. But in general, there's this question about whether language affects thought. And Arrival is actually a very interesting meditation on that, for those of you who have seen that. But anyway, if you are just worried about the fact that they are discrete, it turns out there is a simple way of getting out of that. You can essentially learn word embeddings. It almost becomes like a subroutine. We won't even go into that right now. So essentially, you learn a representation of words as if they are like vectors in some latent dimensional space. The usual way you try to do this is you essentially, you can think of, for example, doing even an autoencoder architecture for that, but which we haven't talked about too much. But there are many other ways, like word vector representations are there. So suffice it to say that you compute the embeddings for words, and that you're going to use that across the board. So you have words become vectors. And the advantage of words being vectors is that nearness in this latent space might have connections to co-occurrence of words. And in general, in language, there's this beautiful idea called distributional semantics, that you shall know a word by the company it keeps. The word basically is connected to the other words that are surrounding it, for example. That's how language works in general. It's not just English, but we'll be talking about English mostly. So it turns out that you can do that. You can basically get some vector representation, think of them as each word becomes some like 1,000-dimensional vector. And there may be, let's say, 30,000 to 50,000 words, and each of these words become a 1,000-dimensional vector. And that's the vector representation you're going to learn. That part is interesting enough, but that's not even the part that we care about. In fact, we'll talk about what we'll do after that. Okay, so the words now are like vectors, just like, so they're real numbered vectors, just like the intensities are. So we are back in business, right? That part is fine. So that's easy enough. But the second is, unlike the intensity of individual pixels, which don't have specific long distance correlations, words do have long distance correlations across a sentence. This is something that's different between words and images. Okay, a pixel here and a pixel here are not particularly connected. What matters in images is in the local macro structure, is this looking like an H, all these pixels making an H, all these pixels making a corner, etc. In language, you never care about that. In language, you care about pronoun references, dereferencing pronouns. So for example, this thing that it should be obvious to you. The restaurant refused to serve me a ham sandwich because it only cooks vegetarian food. What is it? And in the end, they, who is they, just gave me 2 slices of bread. Their ambience was just as good as the food and service. Most of you have no trouble dereferencing the pronouns. And if it's badly written English, then you know that the pronouns dereferencing is impossible. But even the best written English it requires a certain amount of thinking, which we do it automatically to figure out what is it, what is there, etc. That's something that we do. And so we should be able to do that. Otherwise, it's not going to be helpful. And, pronoun reference is the most obvious thing. But, when you're talking about adjectives, a series of adjectives that are applied to a word, like 7 words away, that's another long distance dependence. You see what I'm saying? The pronoun reference is the best way to think about long distance influence in long distance dependencies, but it's also true for other sorts of things in language. In general, they have this stuff, and so because of this, you would start wondering, can I just directly use CNN? Maybe not. Okay. So the next thing is, what is this thing about attention? Okay. And it actually comes pretty fast there, which is, suppose you want to just use an idea like CNN kernels anyway. I already told you the difference between image data and the language data. You keep that in mind. And suppose you just wanted to use CNNs anyway. You could do it, as I said, by just taking a picture, but you could also try to do it in basically in other more sophisticated ways. But the idea would be to start thinking of, so think of, first of all, attention as equal to kernels, except they're very different kind of kernels. I mentioned this already, and in fact, several people wrote this in the reflections, right? So attentions are like kernels, except they're very different kind of kernels in some ways. Okay, kernels are filters. Okay, so what you want to start thinking of attention as a linear kernel, or that is a linear filter, because it's a linear data, it's a sequence data. In CNNs, the weights in the kernel are essentially dot producted with a region of the image. Remember, there's this little square of is a filter with the weights, and you put it on top of an image region dot producted. That was your main operation in CNNs, right? So you want to think of it almost as, I have a linear kernel. I'll put it on top of a series, a piece of the sequence dot product. That's the place you start from. That's like the most obvious place you start from, and then start wondering, why won't it work? What other things are okay? So the weights basically in kernels were learned as part of the backpropagation, right? You know that was one of the things that you did learn. Okay, but the fact that the inter-word correlations are a lot more dependent on the identities of words is a big, difficulty with language. You understand what I'm saying? So you can't just assume that the filters that were being learned in the case of images, they were essentially not dependent on the identity of the pixel or the identity of the value in the pixel, the number in the pixel, right? And yet you would say that, this word has an interesting connection to this phrase. Okay, whereas the very next word may not have. So the actual words wind up having relations. This is how we understand language. Think about it, right? So the question, of course, is, it should be filters, yes, but it should be a filter where the weights are somehow not dependent on the word identities. Or another way of putting it, it should be a filter where the words identities are taken into account in deciding the filter weights. That's attention. That's it. That's exactly what attention is. We'll go into more details, but essentially, if you think of kernels or filters, where the weights essentially in the filter are somehow based on the words themselves. Okay, that's attention. But in doing so, one of the okay, so basically in doing so we need kernel weights to be somehow dependent on the words themselves. And I hope you understand why. Right? In language, it basically matters what word, if it's a pronoun, then it might have a long distance. If it's an adjective, it might have a connection to a noun. If it's a verb, which might have connection to some subject or object or something. Right? So the words actually matter. So you want to get these numbers, these weights that are word dependent, but then having filters whose weights depend on the words themselves makes it a more screwy kind of network. They're actually called hyper networks. Hyper network is one where the inputs in one part of the network actually wind up changing the weights in the other part of the network. You understand what I'm saying? This doesn't happen in CNN. Right? So that's basically what attention is. And so to get what you wanted, which is the filter should be word dependent, you need to actually have, essentially there's linear filters. And when you have a linear filter, when you dot product, you're sort of taking a convex combination of underlying numbers. Right? And instead of calling them filter weights, you want to call them attention weights. Except these attention weights, you can think of them as how much should this word pay attention to this other word 15 steps away, 19 steps away, etc. While in general, the word probably pays more attention to the stuff near it and not as much to the further ones. Because of the pronoun reference, certain words very far away might certainly have big attention. Like for example, the there here has to pay attention to the restaurant. It matters. Everything else is less important. So if you are actually trying to do pronoun reference, you will say the restaurant, blah, 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 there. Okay, and then say, oh, there. And it doesn't matter how many blah, blah, blahs I put in. You see what I'm saying? So that somehow the filter has to realize this weight has to be higher. Okay, and so you would think of the numbers in those filters, basically the weights in those filters as attention. And so you can essentially, we will see in a minute, but you will essentially normalize the weights such that you sum up to 1. And so it's sort of, it's a convex combination. You see what I'm saying? This is basically what attention is. So think of attention as is kernels with input dependent weights. Okay. And the other part, this is the most important part. The other part is how big is the sequence? You could ask about how big is the sequence, that you're looking at. Okay. And the attention depends on how big is the sequence you are looking at. So from the LLM terminology, what is the length of the sequence? Number of tokens. There's a better name for it. What? What? No, what is the number of, like, what's the big difference between like GPT-4 versus like the GPT 3.5 context window. Context window. The context window is the size of the piece of the language you are looking at. You understand what I'm saying? It's not that different from looking at which patch of image you will look at in CNNs. You could take smaller kernels, bigger kernels. Remember, here instead you assume I will take a kernel that is essentially as long as the context window. It's a linear kernel that is essentially as long as the context window. And the weights essentially will be attention. And so you will compute the attention. First, what we'll see, so the rest of the stuff that the pictures that I'm going to show, etc., are from this book. I mentioned that this is a great book that's coming out. It's actually coming out on December 5th, but you have it free on the web. So I'm essentially following the transformer chapter, which, the pictures from the transformer chapter. The connections are maybe more I'm adding, but the transformer chapter is chapter 12. So you can read that. Okay, so there's the actual background thing there. Okay, so these are all the pictures in the chapter. So I'm kind of going to walk you through the pictures in terms of the connections I already have, the broader connections I have, so that you can then read the chapter yourself and say, I know transformers. Okay. So the basic idea is, imagine there are three words, X1, X2, X3. Why only three words? Because I'm assuming in this example, the context length is 3. You understand what I'm saying? If it is GPT 3.5, it will be 3,000 words. If it is GPT-4, it will be 8,000 words. But it's hard to draw those kind of pictures. So I'm trying to explain to you with respect to a three-sized context. Okay, in this three-sized context, there are three words, X1, X2, X3. Each of these words can be drawn from the vocabulary. Imagine there are 50,000 words or 30,000 words. Basically, you have embeddings computed for all of them already. Each word is really a vector. Yes. Yeah, that's what basically happens. What? What are you talking about?
Asking whether the token size only 3,000 if you can slide over an arbitrary.
The point is, at a time, you're looking at 3,000 words. I mean, try to make sense of English by looking at only 3 words at a time. And then you will realize the problem. Sometimes you need to have a longer context length window, even if you're sliding. No, it's basically taking the entire word, right? It basically takes whatever terabytes of English data, which is like a huge big string. So it is doing sliding there. Okay, I understand. By the way, please, I know that this is very interesting to many of you, but because of the time considerations, I may or may not be able to answer every question because I do want to stop at 4 to change the terms. But I wanted to bring this up so that you understand that this is reduced to something that you understand, so that it's not really new. Okay, so the words essentially, notice that X1, X2, etc. These are essentially the embeddings. In this case, the word embedding size is a 4-dimensional vector, right? Normally, there would be 1,020 4-dimensional vectors, or in fact, 4,096 dimensional vector or whatever. Okay, it's a scale. That's the reason why Satya Nadella has to give big bucks to. The idea itself is simple, but doing it on scale with much bigger context and much bigger vector length, you essentially start seeing how much more parameters you're going to learn. And then in doing all this stuff, you remember that anytime they have parameters to be learned, I know that my trusty backpropagation will do it. I don't need to explain to you how the parameter is done. Again, that's the point that somebody actually even wrote, I think, in like civilization progresses by sort of basically subroutine stuff, saying, I know how to do this because I thought about it earlier. Otherwise, if you unroll it, then you'll never get anything. Okay, so what basically is happening essentially is you start with the words and you compute using a single linear transformation whose weights are learned by the network. A linear transformation, what are called values. So this word becomes this value, this word becomes this value, this word becomes this value. The word itself is the original embedding, and the value is essentially computed. The value is a linear transformation, and that's computed. The weights for the linear transformation are learned by the network. Okay, let's assume that's been done. At this point, you have values. Okay, and these values are then used to compute the outputs. And each of the outputs is a convex combination of the values, which themselves are linear transformations of the word embeddings. The embeddings themselves are basically words in this, whatever the latent space. Okay. So for example, here, this word are being combined with 0.1, 0.3, and 0.6 weights to give you this value, this particular output. You understand what I'm saying? Okay, so this is almost by this time, by the time you come here, this is sort of like applying a filter to a patch of image and you get some output. You can ask Rao, what is that output? And I'll say, did you ask me that when we were doing CNNs? Ultimately, all of these are internal representations, and it all depends on what you're trying to optimize. So here basically this word, this word basically, this output depends on the first output, depends on, but it pays 0.1 attention to the first word, 0.3 attention to the second word, and 0.6 attention to the third. At this point, I didn't quite tell you where these numbers came from, these attentions, right? But you kind of know by the time we came here that attentions themselves are computed from the words. We will show that in a minute. That's what makes it hypernetwork concept. Okay, that's what makes it a hypernetwork. So in understanding this, suppose I have attentions, then basically attentions are combined in the values. The question then is, where are the attentions coming from? Attentions are coming from essentially dot producting the representations, the internal representation of the words themselves. That's where this key value stuff comes that I'm explaining. Yes.
So for the attention values, if we want to pay attention to a word like at the opposite.
Remember the following thing. Please stop doing as if you are in the middle of. Ask anytime you're asking a question about, anytime you're asking a question about transformers. Okay, ask yourself what would be the equivalent question for CNN, and would I have asked that myself? Whatever question you're about to ask, you have to ask yourself, would I have been asking which, what should be the weight for which particular pixel being applied? All of that is automatically learned. The problem with language is that people tend to think in terms of, in fact, I showed you a tweet thread I showed earlier later on, that one of the biggest problems in understanding transformers, based on whatever nonsensical YouTube videos that you can find, would be they would use these things like the quick brown fox, jump something, and try to explain everything in terms of these words, appealing to the intuitions. The network uses intuitions. Network basically looks at them as test parameters. And it's not like you're going to be able to tell step by step, oh, it is now going to figure out which word it is paying attention to. That's all going to be emergent based on humongous amount of training over a large amount of data, which is exactly why I like this picture, because it's in terms of X1, X2, X3, not quick brown fox. Because the moment you do that, right, you start trying to solve the problem yourself, as if you are in the middle of the transformer. If you are in the middle of the transformer, you are dead. You have no life. You see what I'm saying? Just waiting for transformer to get done with its training, you already have no life. If you are in the middle of it, it's much worse. It's very important to understand what, basically, you're setting up the architecture so that within the architecture, if in fact the weights are correctly learned, then they would wind up paying attention to the right places. Where is the proof? The proof is in the pudding. Have you ever seen ChatGPT give a wrong coreference resolution? Have you ever seen ChatGPT write a bad grammatically incorrect sentence? We did figure this out. Remember, many of you are familiar, just like I am, and English is a crazy language, right? As you're speaking, you need to make sure that would I say whatever I'm saying here has to connect to what the subject is. The verb form will change based on what subject is. The subject might come much later, and you need to know this beforehand. Most of the time, when some people basically write English where the verb and subject don't agree in number, for example. Okay, and so it's very interesting that just by large scale training, it's essentially getting that. But you are not putting these numbers in. You are making the architecture which will allow it to put numbers. Just like the CNN filters no longer have names. It's whatever gets learned. These attentions no longer have names. They're just learned based on large scale corpora. And if you think you have intuitions about it, I'm sorry, hit yourself in the back of your head and try not to have that. Okay. What you want to ask yourself is, how is attention different from a normal kernel? Why did I do it as a normal kernel? You see what I'm saying? Okay. So then this one is basically, this one is called this way, and this one is combined this way. Now I jump way ahead and look at this picture. I haven't yet told you how the attentions are coming in. very easy. But notice that once you do all this stuff, essentially just like CNNs, remember CNNs, there'll be banks and banks of CNN filters. Just like that, by the way, in the attention case, it's called an attention head, and you can have multiple attention heads. And the multiple attention heads are like a bank of. So you have a bank of filters followed by something, followed by another bank of filters, followed by something in CNN. You can have multiple attention heads, followed by some, some normalization stuff, layer norm or something, followed by another bank of attention, and then multiple attention heads, and so on. So it's very similar to the CNN architecture, except you call instead of kernels or filters, you call it attention, and instead of filters, you call it heads. Okay, because it has this nice Turing machine-ish thing that I'm looking at a word and how much attention is the word paying to other words somewhere else in the sequence. Okay. Now interesting question is, remember in CNN, you do this stuff, and at the end, if you are trying to do classification, you take that last level representations and you throw in a perceptor, multi-class perceptor. Right? And I'll show you in a minute that transformers do the same thing, especially transformers can be used multiple different ways. The one that you guys care about is LLMs, which are essentially what are called decoder-only transformers that essentially just try to use these internal representations. At the last edge, they try to predict the next. So they're essentially computing a multinomial probability distribution. I'll show you a picture of that. Okay. And then from that, you sample the next. Right? That's how LLMs work. I'll show you that next. But before I go there, I want to ask you the following thing. When you are trying to predict, when you're trying to understand a sentence that's already been spoken, or a book that's been written, you do look backwards and forwards from the word. Right? But if I'm trying to predict the next word, I can't say, let me also look at the future. Because that would be cheating. Right? If I give you the entire sentence and I say, here the first word, what's the second word? Oh, the second word you said is this, so I'll put that. You understand what I'm saying? So what do you have to do? You have to make sure that the internal representation that you're computing don't depend on the future words in the sequence at any given point of time. If you are going to just predict the next word. If on the other hand, you're trying to do things like translation, that would be a encoder-decoder architecture, where when you're translating from one language to other, other than quote unquote Americans, everybody has translated because in their head as well as because they know more than one language, right? And so you know that when you're translating, you read the whole thing and then translate. You don't just translate word by word by word. You go back and forth. So this view actually makes sense for the more general case. If you're only looking at just giving the next word, which is what LLMs do, then they should look at the future. So what do? You say, even though I have these attentions, I will not let the future words affect me in deciding the value, the output. So in particular, anything that's an upward arrow, because this is x1, x2, x3, any upward arrow is about future. Right? It's about a word that you haven't yet seen. Because there are only 3 words here, then there's like here there are 2 upward arrows, here there's like 1 upward arrow, here there are none. So every upward arrow has to be zeroed out and you have to renormalize that attention. And that's what is called masking. So you may have heard of masked attention. All it is doing is, if you are trying to predict the next word, just predict the next word, then you should be looking at the entire sentence when you're training to predict that. Okay, so things fall into place essentially from just this notion of attention. And the full attention is needed if you're trying to comprehend the entire sentence and translate it into some other language, etc. Okay. So I mentioned that the value here is this word linearly transformed, right? And so it turns out that actually you do 2 linear transformations for each word. You learn 2 linear transformations for each word. Okay. In fact, these linear transformations, by the way, are the same for all the words, but there are 2 linear transformations. Okay. One is the value and one is the key. The value is the one we have seen till now. And for reasons that are not that important, honestly, you wind up doing many things in any of these CNNs or transformers. They're just design decisions. There's no huge theoretical reason as to why you should do it that way. Like there is a theoretical reason as to why the weights have to depend on the words. That you understand, because it depends on the data. Many other things are not really that, like they're reasonable assumptions. How many heads should be there, for example, and how many sequences of multiple heads should be there. Those are all just random design decisions. Okay, so including that, in fact, one of the other things is the key value pairs. And so what you would wind up doing is, in trying to figure out an attention a word has to apply to other words, you use its key and take the dot product with the other guy's values. Okay, you could have done value similarity. In general, if you do dot product, if you hear dot product, think similarity. That's what dot product is. Right? So instead of essentially doing value dot product, you do key value dot product. So you wind up learning 2 different linear transformations. The specific numbers in those transformations are learned by the backpropagation. Okay.
What's the point of the query?
That's what I'm saying. So this terminology comes from IR, etc. So this is like there's no real big reasons, people get all glummed up on that stuff. That's less important. It's basically you need word similarity to figure out the attention you're. And the word similarity is not at the level of bear and restaurant. It is, notice the interesting thing, it's not even the word similarity. Word value similarity. The word embedding doesn't change from one sentence to other sentence, but the word value could change. You see what I'm saying? So anyway, and then after you get this, then attention itself is essentially doing a softmax. Attention, basically becomes a softmax between the key of one word and the values of the other. So you take the dot product and then you normalize them. And the way you normalize them happens to be that you take this nonlinear normalization, softmax normalization. One of the weirdest things is in the normal transformers, there is no ReLU, there is no sigmoid, there is no nothing. Key is a linear transformation. Value is a linear transformation. Where is nonlinear? Remember, I made this huge thing that if you just make linear all the way, it's just a one big linear. Some nonlinearity has to be there so that you learn nonlinear. It turns out the weirdest thing is this is the only nonlinear portion. Okay, this is the only nonlinear portion. And that's enough. As long as there's some nonlinearity in the network, it can learn nonlinear functions. Okay. So that's about how that attention is paid. So in essence, basically, it's the same picture as earlier, where you are taking the words, you are taking them, converting them into values, and then the values there are converted to the outputs by essentially using the attention weights, where attention is this, which is computed as in dot product normalized. Okay. I looked at this picture and decided Simon Williams should be paid a princely sum. Okay, this, by the way, this guy essentially spent his huge number of years. I don't even know, but I just think this is what having a passion do. He's not doing startup. He's writing a textbook so that all of you can understand beyond, beyond the And he's basically not even making any money. Nobody ever becomes like textbook. I mean, like if you write like deep learning for dummies, you can become at least 1,000 a day. Okay, you say deep learning fundamentals, none of you will actually buy them because you're also poor students. You try to get the PDF. So he's just giving you the PDF free. You have to ask yourself, what is this guy's reward metric? And you have to understand you need every different kind of reward metric for this damn world. If everybody is like you, the world will go down. Not necessarily because you're a bad guy, but because you need all different reward metrics. Okay, so I love this picture because it's a lovely, nice thing to explain what we just said, that you're starting with the same x1, x2, x3, and you are essentially computing the keys, which is a, this part of the network are keys, which is a linear transformation. This part of the network is values, which is a linear transformation. They're being dot producted and then softmaxed. That becomes it. And this picture tells you it is a hypernet. You see what I'm saying? And ask yourself how many people have made Bozo YouTube videos about transformers are this. And many of us, many of you maybe watch them and say, yeah, Mom, I know transformers. This picture is way more useful in understanding what actually happened. Okay. So anyway, so you can live with this world without understanding how the world works. You can make AI millions without understanding how AI works. Okay. I'm hoping that you would be not so much trying to make money without understanding how things are working. In terms of this course. Anyway, so this is a lovely picture. Spend time, reading that part of the thing, because it's essentially telling you whatever I said in words in nice pictorial form, and except it just makes the whole thing come alive in terms of the hypernetwork nature. Okay. So this is, if you do this, okay, sorry. Yeah. So basically, this is another way of writing the same thing. I'll go back to the thing. This is another way of writing the same thing. I computed the queries, I computed the keys, I computed the attention, I took the values, take the attention, and computed the output. This is more the picture that people show you, but this is a way better. But then, having done that other picture, then I'll say if this is one attention bank, one attention filter, I can put one more attention filter. That would be multi-headed attention. It's just a filter bank. You see what I'm saying? You understand things by understanding pieces and repeat the structure. Okay, just as you could put multiple filters. Remember in CNN, you could put multiple filters. Once you understand that, I don't need to worry about who learns the numbers, network, the filter weights. I can put more of them. Okay, and similarly here, once you understand how the attention is being computed, essentially it allows for very different linear transformations to be learned as keys and values, and then those wind up giving you different attentions in different heads. Do you see what I'm saying? All this is very nice, actually. And so by now you already know multi-headed, and a couple more slides I want to show you before we are done with transformers. There's a problem. There is a damn problem. There's a damn problem, which is in many languages, words, positions don't matter. Lots of people from India, they know that you can change the sentence in such a way that you can basically, in a sentence, you can change the order of the words and the sentence will mean the same. It might look awkward, it means the same. English, oh my God, the Bozo language, it's not function. Tom picked John, John picked Tom, completely different stuff. Right? That's why it's called a sequence data. It's not just a line of pixels even. It's a sequence data. So that's one other thing that I should have, I think I mentioned it in the first two slides. The thing that is different about images and this is essentially that A, it is linear, and B, the attention depends on the word identities, and C, the word order matters. I found embeddings for words so that it doesn't matter where the word is in the sentence. How do I make that somehow take into account the position? The simplest way would be, the simplest and the most reasonable way would be that word and position are together taken. And basically don't combine them randomly, just here's the word, here is position. You see what I'm saying? So it's like everything should be some function of the word as well as the position where it is appearing in the sentence, in the string. So imagine that for every position you come up with some vector. It doesn't even have to be learned. In fact, the original transformer paper came up with some positional representation based on sign. The interesting question is, I would say put that position, and this is the vector representation of the word. And then the first thing before I look at the other side, people say, there's a vector, you have to add them up. Here are elements, here are the vectors, add them up. Makes no sense whatsoever. Makes no sense whatsoever. You essentially took a word which has the same embedding across all the sentences, a positional information of the word, and added the two vectors arbitrarily. Because the dimensionality, you made it to be the same, so you just added it. If you ever want to question, if you ever want to say, if you ever want to kind of convince somebody that deep learning doesn't have clean theoretical foundations, this is one. Makes no sense. Why are you doing it? The only answer is, what do you want? ChatGPT, don't you like? And it does that. You understand what I'm saying? This is ends justifying means. You understand what I'm saying? That's not the way to actually justify anything. But that's exactly what happens. It works. If you don't like it, you're like an un-American, non-ChatGPT kind of a person. Go somewhere else. It's the same thing for any bad thing about the society. You'll say it's a bad thing. You say, what's wrong with that? America is doing well, so it can't be a bad thing. Right? That's ends justifying means in general. But that's what is happening. I'm not necessarily making a particularly dramatic thing about it, but I want you to understand that there is no theoretical basis for adding positional encoding vector to the word dimensional vector. Do it because you're out of ideas. It seems to make it reasonable.
They have a very weird justification for it.
Yeah, I mean, yeah, it doesn't make any sense. Okay. Last couple of slides on transformers. Okay, so a transformer network basically looks like this. Just as in a CNN, you have a filter bank followed by some pooling layer, followed by some relay layer, followed by again filter bank, pooling layer, relay. Instead, the structure would be more like this. Essentially, you have multiple heads, okay, followed by a layer normalization, which is sort of like batch normalization. Okay, it's not critical, honestly, it's just there. It's a useful thing. Many things seem to be working. Why do you care? Okay, and then essentially, so you can repeat this multiple self-attention many times. Okay, and then the last thing is, if you are using it as an actual LLM, then at the end of the whole thing, at the end of this transformer network, right, you are using the context window to predict the next word. So what you do is you actually train the network to minimize the loss in terms of predicting the correct word that you have actually seen in the training data. Okay, so the network setup looks like that. That's your last layer multinomial perceptron, where the multinomial perceptron is basically going to predict which of the words are more likely. You understand what I'm saying? So it takes a context number of words, and then it tries to predict the context plus one word, which has to be both the words in the context as well as the word you're predicting that will be in the vocabulary. You can't make up new words, right? I mean, that would be great if ChatGPT started making gobbledygook words in predicting. And then I don't know what you guys would do. You probably say maybe ChatGPT is like. But the point is, it has to predict the words that are in the vocabulary. And that's just basically, so notice that this part, look at the symmetry between CNNs doing classification on the objects and transformers doing classification on the word that comes next. Okay, so that's your transformers with attention, with the head, multiple attention heads, and essentially the last part being CPTs. So we mostly talked in terms of the CPTs. When I said LLMs essentially tell you the CPT table for the last word, I didn't tell you how they computed it. This is basically how they correct. And since transformers are working for language, they try to use it for everything now. That's a different story. Most of the nice intuitions I gave you actually work for language. I haven't yet heard in music, in musical notes, a note here kind of making a slight reference to a note that happened 15 seconds back. I haven't heard, maybe because I'm told deaf or something. Okay, if you don't have that, then I don't quite know why you need the attention network for that. But you already have it. What was the thing? For the guy with a hammer, everything looks like a nail. Okay, and so by the way, one other thing is that images. You think images are basically two-dimensional. But I have a transformer. I want to use a transformer line. Well, do it raster scan. It'll be a huge, long, big sequence. You know what I'm saying? That's basically vision transformers. I don't have time to show you those, but yeah, basically that chapter talks about vision transformers too. And it doesn't do as well as CNNs, honestly, because it doesn't. Again, you need to take the inductive bias that makes sense to the data. And the bias that makes sense to image data is essentially features are based on the local macro characteristics. The bias that makes sense for the words is that they attend to each other over long distances. You see what I'm saying? And so if we use it, the right bias, then you're likely to get better performance, quote unquote. So this is your summary. The data for CNN to transform, this is your cheat sheet. CNN pixels in 2D, this is word sequence in 1D. There are local macro correlation between pixels. There is long distance word specific correlation between words. There is no ordering between pixels. Word token order matters in many languages, including English. And in terms of processing blocks, you would have CNN kernels or attention heads. Attention is the name that you give to a filter whose weights are essentially equidependent. And the filters whose weights are learned via backpropagation here, filters whose weights are dependent on the words themselves, actually word values plus positional encoding. Because remember that attention is on top of the values, keys and values. Okay, I honestly don't have a great explanation as to why you need both keys and values. It's like it works. You see what I'm saying? But I can have a great explanation as to why attention should be dependent on the inputs. That's why I use that a lot more. Okay. You can have banks of filters, you can have multiple attention heads, and also the other thing is nonlinearity comes from softmax, which is not obvious. That's only And then where are all these numbers coming from? When you say the gazillion parameters for like 176 billion parameters for ChatGPT 3.5 or trillion parameters for the other one, it's because essentially you have to realize, first of all, attention is quadratic. But every word needs to know what attention it has to pay to every other. Okay, plus there are these linear transformations which have parameters. And that's what the ones that are being done. Okay. So this was like 21 tweet that I did, about how to explain transformers. Believe it or not, you paid tuition and you felt sad that you had to watch old lectures. This is completely new lecture. I never gave this. This is the first we hear it. Okay. So you can at least say that it made one lecture here. But I mean, I've talked to my students about this. I mean, one of the points I made is don't use speed from class example. Use W1, W2, W3. Instead, I use X1, X2, X3 because that's what's happening in slides. You understand it at that level, you really understand. If you understand it based on fifth round facts, you are essentially anthropomorphizing the way you understand language. And the way you explain to yourself how you understand language. Because the way we understand parsing, we do parsing is a tacit knowledge. We don't really know how we do. Okay. So that was that. And one of the other very interesting things, several people actually asked about it before. That, by the way, is a recurrent neural network. And normally the first idea that people have for sequences is recurrent neural networks. And the problem basically is that the recurrent neural network's length has to be in some sense proportional to the context. It becomes a very long network. Sequence is built into the network. What transformer did is parallelize the heck out of recurrent neural network in a very bad way, honestly, by just saying they're all words, but you just add your position information to the word. Then it's no longer recurrent. Why is it? Now, how could you do this? Hey, like checking. But it's a very useful thing. And in fact, I make this very interesting. I mean, to me, interesting and may not be for others, but probably for you guys too, is that the useful off-the-wall planning graph analogy. You guys heard of planning graphs in this class, right? The graph planning graphs where you kind of remove the interactions. And planning graphs allow actions to be put parallel because they're ignoring the interactions. By ignoring the positional information, you allow words to be processed in parallel. And then you just add a little positional information. Bag of words completely ignores the positional information. RNN fully takes positional information into account. Transformer is somewhere wishy-washy. That's the way I think. Again, my point of doing this is connect everything to everything else. That's the only way you will remember until you become full-blown place of dementia. Hopefully, everything has to fall down together. And so, you won't miss anything as long as you make the connection. I mean, there are actually people have shown that people who actually are, spent a lot of time reading and understanding the world have, they have slower downtime, slower, when they get dementia, they lose their abilities in a slower pace than normal people who say, why should I read it? Okay, because you connect things, it's actually quite useful. Okay, parting thoughts. 5 minutes parting thoughts. So those are the introduction stuff that, so these are the lectures we did. And actually, just to remind you, this is the one, right? Because that wasn't there in the midterm one. So it would be there. The problems for the midterm 2 would be from that. I won't be asking you questions on transformers. It's just a part of the because you wanted it. Okay. And I recorded this. I'll put the lecture up, hopefully. Okay. The other thing is, and what basically we tried to, so the other thing is this is a, Kaya spent time doing a word cloud analysis of your, answers to all your questions. This is a bag of words. We haven't yet done the ChatGPT analysis. That will come next. So list 5 or more ideas. There are networks. Of course, she could have removed things like and can. Of course, this can reminds me of Obama. Yes, you can. But of course, neural network, and then really this long a class, etc. But anyway, so there are things that you can make sense of in terms of the things that people like. 3 non-trivial technical details, value function. By the way, Q star is a value function. It's a value function split into actions. Some bozo who was trying to explain Q star tried to make this statement on LinkedIn or something that, unlike normal, unlike learning which action to do when, Q star is much better because it doesn't depend on the number of actions you have to do. And you guys will read this and say, the influencer tick. Instead, there should be an untick for this thing. You see what I'm saying? Q does depend on the number of actions. P doesn't. Right? Okay. So value function, Q function, Bayesian networks, heuristics, various people learn things, at least there's no random words there. Transcending things, apparently learning. You can, I put this up so that you can look into it too. I didn't really do major analysis yet. I can give it to ChatGPT and see if it finds anything. That would be a useful thing to do. And then list 0 or more jokes. Jokes was the biggest thing. Part 5 is 1 or more idea topics. Those were the ones that I started. Basically, there were several people who did want before as well as, plus, since I brought up LLM so damn many times, it's worth understanding how is it, what at some level, just as CNN is right?
Transformers.
What?
Human transformers.
No, that doesn't mean again. And he is converting image data into sequence data. There you go. Right? I mean, yeah. So yeah, you could be the human transformer for the AI world. Okay, so the last thing is, if I have to do it all over again, so clearly this is like the first time I did this type of a class, as I mentioned multiple times, where you watch the lectures. It was actually a mistake because I asked them to give me once a week, 3-hour class, and they misunderstood and they basically made it into a hybrid class. Okay, but I want you to understand that as much as you may have hated it, I can make you laugh for 3 hours instead of 1.5 hours, but laughing is not what you took the course for. The time that you spent in watching the videos and then writing your reflections and then giving me questions that I can answer, honestly, you probably could be the batch that understood more than other batches, unless they spent a lot of time, because you've been forced to some extent. So I would not change this, honestly. In fact, I was going to basically, what I would do is in-person class time. Basically, this is what I still want to do this, and I want to use in-person class time to answer questions and elaborate. Because look, you guys want me to tell you diffusion models, transformers, this and that, LLMs, Q-star, and how many things are you going to put into like a intro AI course? Yeah. Seriously. And the reason we could put a lot of it is because I have this additional, extra time, basically, that I could bring in. Okay. So if I were to do it all over again, I would do this, except I might want a weekly meeting more than 1 hour 15 minutes. Okay. And I know that many of you wanted more for many, many things, whether you really meant it or like more reinforcement learning, more this, more that, etc. I don't know whether you really meant it or not, but if you really meant it, think of this as the introduction to deeper study in those areas. Okay, you have basically a bigger picture of connections across areas. Okay, and you are like, unlike people who are currently discovering that Q star and A star are connected because Sam Altman has this conspiracy, you knew this 3 months back, which is like 3 million years in the pace at which AI progresses. Okay, so that is that, and so you can, and I hope basically you enjoyed the course at some level, and you can keep in touch. I spend a lot of time writing stuff on AI stuff on both, mostly Twitter, but also LinkedIn. You can follow that if you're interested. You can, of course, send me an email, rav@asu.edu. My office, many of you have never seen it, but it is in the Brickyard 560. It's not hidden or anything. It's not a latent office. It's a real office. Some of you have come, most of you haven't come. That's probably the sad part of teaching a large class. I'm used to knowing everybody's name. Okay, and for 127 people where we meet once a week, it's very hard. Some of the people who spoke up, I know their names. And honestly, it's hard to give a bad grade to people that you know the names of. It requires extra effort. Right? Whereas if I don't know you, hey, I don't care. Just name. Honestly, in life, that's important. The FaceTime is important because it's like there's a hilarious thing that I will send you after this, where remember the Microsoft what is that, the paper clipping. So there's this, how many of you have seen the Saturday Night Live sketch on clip? I will send it to you. It's serious thing where this guy tries to remove the clipping because he gets irritated. And it turns out clipping is the man. I mean, this is nice guy and he starts clipping around. And then he says, I have this daughter who I'm trying to, she has all these problems. I'm trying to help her. Do you still want to remove me? If you want to remove, just go here and say, kill clipping. And then he does it. Right? So you basically put a name to the face. It's good in terms of life. And so I wish I knew more of your names to faces. But so be it. But I had fun taking this and have a good rest of your semester. And I'll see you again next week for the exam. Thank you. What?
What's your third language? Telugu and
Actually, 4 languages: Telugu, Hindi, and English, and also Bengali. I know somewhat because my wife is Bengali.
oh, that's
Yeah.
all you know.